Can everybody hear me? Great. Yeah, so thank you, Phyllis. And yes, this project, it's called the Evaporative Cooling Project. And it's a project that was funded by a 2023-24 major seed grant of about $12,000. And it was kind of co-financed by both ICAT, but also the Center for the Future of Workplaces and Practices, which is a really great center and one that I would encourage any of you who don't know about it to look it up. But I'm just very grateful for the funding so that we could work on this project. And today I'm going to tell you about it. So let me start a little bit with the team, because there were a lot of people kind of coming and going. There are 3 principal faculty members. There's me, I'm Brooke Kennedy. I'm an associate professor in industrial design. I worked very closely with Stefan Al, who was here full-time as a faculty, but he's now at Hunter College in New York, but still maintains an adjunct position here. And then finally, Georg Reichert, who's he's the program chair of the Myers-Lawson School of Construction, and he brought a lot of sort of technical support and knowledge to the project. And then we had a bunch of students who were indispensable and much needed to make all the work happen on the ground. Those include Saeed Sekhtari, who graduated about a year ago, a little bit early, and is in Chicago. There's Alon Farahi in industrial design, who's sitting right in front of me. Alon, please stand up just for a moment. And then Muhammad Ali in architecture, Aditi Hadkar, Faraz, and Nick Adams, another industrial design student. So let's take a step back and talk a little bit about the context, kind of the impetus behind this project in evaporative cooling. So as we've all read in headlines probably over and over again, we hear a lot about the planet warming, but we also hear about extreme heat events and the effects that it has on people. So heat, of course, is not necessarily always comfortable. We don't necessarily like it when it's extreme, but I think more importantly is that it can be deadly. And so efforts to kind of control and manage heat, both for human comfort, but also not only humans, but also other organisms, but it's also a matter, in some cases, of life and death. Just a few more images to show you here. I went to college in Portland, Oregon, and a few years ago, they had temperatures in the 100 teens for a few days, which was completely unheard of when I was there. It's showing some examples. So I think in some ways, one of the obvious kind of solutions, or what people think about, is, well, if the planet is getting so warm and there are health effects and dangers to it, why don't we just all use air conditioning? Well, air conditioning is wonderful. It makes us feel great. It's a luxury, and a luxury not everybody can afford. It does have caveats, though, especially in terms of the use of energy, because it uses an awful lot of it. That right now, here in the US, about 19% of electricity consumption goes towards air conditioning. And it's about 7% globally, but of more interest is that air conditioning is set to triple or possibly quadruple in the next 25 years as other countries start adopting it in order to be comfortable, but also for their safety. So, I mean, this is something just to muse on for a moment. I think air conditioning is often kind of singularly focused on as sort of a solution to environmental heat. One of the areas that this project is really focused on or based on is trying to understand ways to make spaces, buildings, do better at cooling themselves more passively. I know that a lot of you are in architecture, and I'm sure a lot of you have studied the passive house movement. There's a lot of research about making buildings better at cooling themselves passively through any number of techniques. And some of these techniques, they're very old, and in some cases they've been forgotten. They're sort of off the radar, I think, of planners and governmental agencies. And here are just a few examples. You see examples of evaporative cooling systems. There are others that have certainly preceded the one I've worked on. There are things like Zir pots that passively cool in the manner of refrigeration. There are botijo. There are wind towers, which Eamon in interior design has focused on. She did a great project for ICAT about this. And many more. I could go on and on and on. And actually, I do go on and on and on. I wrote a book that was published about 2 years ago, a year and a half ago, called Reimagining Alternative Technology, which really sort of surveys kind of a lot of these types of passive technologies that are kind of invisible or have been forgotten, and asks the question, I mean, could these technologies be redeployed to participate in sustainability discourses today, which I think the answer is yes, but it's really an exploration of these technologies, not just heating and cooling, transportation, materials, lots of other things that is sort of the foundation of a lot of the research work I do. So, as I mentioned before, wind towers are kind of like one of the rock star examples of cooling. There's been a lot written about them. They're not perfect, but they are effective in being able to cool, especially in arid environments. They originated, most scholars think, in Iran, but they exist in a lot of other countries too, especially in the Middle East. And in part by sort of collecting wind and breeze to circulate air and expel hot air. They also rely on an evaporative technique by using water that's underground to help cool the air. Interestingly, a recent architect project, Francis Carre, who won the Pritzker Prize, I believe in 22, which for those of you who don't know, but there are a lot of architects here, so for those of you who are not architects, the Pritzker is sort of like the Oscar of architecture in terms of awards. And in many ways, even though there are some other influences like termite mounds, there's a lot of similarity between this building in Kenya and wind towers. It's really a fascinating passive cooling technology. Moving on. So, I mean, evaporative cooling sort of was developed around the same time as air conditioning, and in a way, air conditioning sort of pushed it out of the way because it's more effective. But still, evaporative cooling exists, although kind of quietly and in a hidden way. These are more mechanized evaporative cooling solutions. They're not passive like the ones I'll talk about, but just there's a swamp cooler there on the left. Actually, and humorously, a lot of cars back in the 50s had these weird-looking sort of, you know, torpedo-firing looking evaporative coolers that would attach to your car. But more close to home, on the right, I took this Google image of the Blacksburg Library, and they have a mechanized evaporative cooler behind them. This is on, I forget the name of the street, I should know. But if you look, you can see that the gutter is channeling water into the machine. And if you walk by it sometimes in the summer, it sounds like a waterfall because it's using water. But for us, kind of more specifically, and get down to the project itself, this is a project that a lot of other researchers have been interested in. It's called Moscates. I don't know how to pronounce it properly, and there's actually, surprisingly, there's some research about these, but not a huge amount. A couple of architects at UC Berkeley, Rail, Sanfratello, did a project based on these. But as you can see, there's this kind of pot that's circled in blue that's sitting out on a windowsill, and as air passes into the space, it passes over the pot and cools. It cools because it's full of water, and the water evaporates, thereby transferring heat. So it's kind of funny, in a way, the image on the left, it kind of looks like a window unit, right? From a long time ago. But this is one of the examples that we drew from. Okay, so let's get more into the project itself. And it's really an overview. It was hard to kind of edit down what exactly to show, but I'll try and show the overall arc of this project and its potential. So we'll talk about what we did, how we did it, What did we learn, which we learned a lot, and what's next. So this is a piece actually that similar to what Alon had worked on last term when our team had shrunk because a few people had graduated and moved on to different universities. So the goals in this project really were to try to create, kind of like the Muscatesi, a series of, I guess you would say, columns, which could be lined up in an array and put into a space. Exactly what kind of space is still undetermined, and then using cross-ventilation or passive breezes or mechanized breezes would pass air over these vessels, like the Muscatesi, and cool the air. And I didn't mention before, but there's a lot of, even on the Department of Energy website, there's a lot of information about how effective evaporative cooling can be and how it can reduce temperatures by 10, 20, 30 degrees Fahrenheit. Mechanized, but then also more passively as well. But here, going back to this project, we're really exploring using clay 3D printing, how to make these vessels evaporate better. So the vessels are filled with sand and water, and through modulating the surface, both in terms of surface area, the texture, which is something you can do with software like Rhino and Grasshopper when you're printing, can actually change the efficacy by encouraging more water to evaporate. So initially, it was sort of a classic kind of ideative process of exploring different types of form factors with different qualities, all sort of around, we really focused in on these sort of arrays of columns. They're not columns in the sense that they're load-bearing, they're columns in the sense that they appear like columns, their proportions, they're taller than they are wide. And so looking at different surface textures, also making them more porous in form, and even we thought a little bit about integrating plants or other types of natural greenery, which could be fed in part by the water. So we had far more ideas than we could possibly test, but we had a lot of fun with this. And this shows a little bit more of some of the ideation more concretely in shapes that we could evaluate, narrow, and then ultimately print and test. So this is just a few images of the few different types of pieces that we started to print, and we printed them in scale. We'd hope to print something more full scale. We still hope to do that, and we look forward to as a next step. So it shows some of the different form factors here, and then on the one on the right, you can really see the texture. It's a little more prominent. And so as I said, I mean, there's a lot of kind of digital workflow going from CAD to Grasshopper to a CAM program and ultimately printing. And you can see that from the upper right, that almost looks like sourdough bread. When you roll clay or roll porcelain or any other clays with water, it sort of has the consistency of sourdough bread, which actually you could 3D print sourdough bread with this machine that we have out in the RDF. It's a WASP 3D printer, an Italian fairly large scale printer. And we've tried to print a bunch of other stuff also in the biodesign lab in the media building. So here you see Alon and Saeed. And the one in the lower right, they're sort of smirking because, yeah, it has the tendency not to do what you want sometimes and wipe out. So just some more images. Here you see how sand is placed inside. We needed more lap joints to kind of hold them together so they could be stacked. But this is some of the work that we were engaged in. And so like I said, we sort of tested different ways of trying to get the vessels to evaporate more efficiently. We used a humidity chamber. We also used some infrared, an infrared camera on loan from the Myers-Lawson School to sort of test heat. But this is sort of the overall schematics about how it works. It's a little bit of a Muscatesi and a little bit of a Zierpot in this. So we further on developed a shape after testing and went more with a shape that had the surface texturing over a porous one. I think the porous one might have worked better. There were more complications in 3D printing it, so we went ahead with the one with the texture. This image to the right is not a piece that we have anything to do with, but it was one in the RDF. But I think it sort of shows how texture can really be explored aesthetically, definitely, but also for the purpose of evaporative cooling. So here you see a little bit of a proposal about how a series of columns could be placed within some kind of sort of Mesian style pavilion or some other type of structure. So I use the Mesian pavilion as just a simple placeholder, showing some shade so it's not just a greenhouse box, but with the idea that the columns could be placed centrally and that through ventilation or fans would pass warm air over these to make them cooler. So I'd like to show you just some visualization of what this could mean. So instead of, I mean, very often, as you saw with some of these examples of evaporative cooling, so often cooling and AC, it's sort of hidden behind the box. You know, there's central air in this building, but all the mechanicals are sort of hidden. In the case of the library, it's a big box sitting behind the library, and often these things, air conditioning is not integrated, it's added on afterwards, and it's in a way not, it doesn't enhance the design of a building or a space. But with this direction, we're thinking that it could, especially if you could use gray water. Possibly in some climates, you could use rainwater as a way of filling these columns or partitions full of sand. Just show a few other images. Kind of went a little nuts with some of these images. But sort of the idea that there could be this like little nook where you could go and sit, meditate, read, etc. On a warmer day, and being surrounded by these sort of more sculptural columns, you could cool in the process, sort of a cooling space, as opposed to a fireplace. It's like a Julius Schulman style image. So at the moment, from the work that we've done, we've gotten a fair amount of attention. I gave a talk about a year ago at the Technical University of Munich about this technology and others, mostly this, but also about the book, which is the underlying sort of impetus and research direction. And we got some other nice publicity. Fortunately, wasn't able to go to the ICAT conference, but the work was also exhibited at the Coalescence conference in Richmond. And there's a nice VT News article about it, so you can learn more about it there. So I'll just say a few more things, and then I'll take some questions. There are a few different directions that I think we could go in next that I would be very excited to explore. One of them is that we noticed, that there are some cases where a piece like this could act as a stool. How it would be covered is to be decided and figured out. But especially in shady places, we noticed that a lot of the pieces, when we would fill them with sand and water, they got really cold. So actually almost sitting on one of these things could cool you through direct contact. And had a student, Nick Adams, who explored this a little bit. Also thinking a little bit more about making the columns more directional and aerodynamic. I think perhaps it's a slightly newer area of research to think about the interior aerodynamics of a space and how to channel and focus breezes and wind and air movement. And so to that, I'm sorry, here's another picture of kind of a stool or like an outdoor piece with shade. This is just a sketch of trying to make the columns a little more directional to move the cooler air more widely. Another area that we're probably going to investigate is that we've been making some experiments with kind of biomineralized ceramics. Now, I won't really go into this a lot, but what this means is it's a type of process that you can use that emulates seashells. Same way seashells are made. I mean, in a way, seashells are almost 3D printed if you look at the layers of them if you go to the beach. But they do it without having to put them in a kiln. And there's a lot of research now starting to focus on this. Georgia Kenichi in architecture, I know, is very interested in this, and we've had a lot of conversations. I've worked a little bit in this area with 3D printing, and we're thinking about this as an application to show a good example. If you're trying to cool spaces, it would be not so nice if you had to heat up a kiln to 1200 degrees in order to make the things. And the last thing is we have a patent disclosure on something related to this that I couldn't show, but a lot of stuff came out of it, which is still going on. And to that, I'll say thank you. That's all for now, but stay tuned. Those are some of the team. That's Saeed, me, there's Mohammed, and Alan. I didn't have a picture of everybody. And to that, I guess I could take some questions.
Thanks, Brooke. That was beautiful. So one thing I've thought about my whole life, either living in the Deep South or very cool climates, is mold.
Yeah.
Does this have any influence,
Yeah.
pro or con, on mold inside in interiors?
It could, but in the testing that we've had, we haven't seen that to be a problem. I'm not aware that that's a problem with evaporative coolers, even the mechanized ones. You do want the water to move and not stagnate. But I think mold is especially a problem in more humid environments. And a lot of evaporative cooling, it's true, it works better in drier environments. So we're talking about, at least in the United States, the American West, or in more high up altitude places. So, I mean, that's something that you would have to design for, but it's certainly, you can circumvent that for sure.
When you're looking at gray water, not necessarily rainwater, there are often minerals in that. Mm-hmm. How would you combat mineral depositing on the clay if it's running through that system?
I can't fully answer that question. I mean, I think the sand or the aggregate that you put inside could have a filtration quality as well. I didn't mention that. But ultimately, it would pass through, and the minerals, it would have to be filtered to some extent before being passed through. But certainly, there are a lot of water sources that could be tapped that are already in a building, so you don't have to use fresh water, which is especially a problem like, say, in Arizona, or if you think about places like Los Angeles, where, of course, the fire hydrants didn't work in the one moment that they were really needed.
So since you were saying that you'd want the water to be like constantly flowing, would this, like, for example, inside of a house, would it be something that like year round it would be like working, or is it something that the homeowner could turn off? And
Great question.
like if it's the middle of winter, would they even want it like going?
So I didn't picture it in some of the images, but we sort of envisioned that there would be some kind of faucet, whether it would be electronically controlled or it could just be some very beautiful analog faucet kind of near the system where you could just turn it off. Because of course, there will be a time where you might want to turn it off, especially when it's cold. But also, I mean, some evaporation can provide some needed humidity, especially when it's really dry during the winter. So, but yeah, you would want it to be purged. You wouldn't want it to be standing for the same reason that Lisa had asked before about mold. So I think in some ways these images are they look somewhat realistic, but there's certainly a lot to sort of detail to figure out, but I think it's really more the kind of broader sort of thought or vision that, you know, could cooling be more sort of aesthetically integrated as a part of a space or a home, et cetera. But that's an excellent question, though. Thank you.
Thank you so much for the presentation. It was absolutely fascinating.
Thank you.
My question is, a large percentage of the world's population lives in climates affected by climate change.
Yeah.
How could these technologies be introduced in these communities, most of which are in extreme poverty?
Yeah. No, I mean, that's an excellent question. I mean, one of the big problems with AC, of course, is affordability. It's not desirability. You know, some of these technologies, they come from the countries that could use them and are not using them as much as they could. So I think that there's a level of accessibility, and especially the fact that electricity is not needed. I mean, there are lots of parts of the world that still, of course, don't have electricity. So I think in some ways, I think that could be a benefit, but I mean, that's a really excellent question, because accessibility at a global scale is needed, and that's really the people who are suffering the most in climate change are not in this country. It's all over the world.
I have one that I like to ask.
Okay.
Can you talk about how your team worked across disciplines?
Great. You know, it worked really very seamlessly, especially within the disciplines in the college, because in a way this was sort of a meeting point somewhere between furniture and architecture. And then further, some of the support that we got from the College of Engineering, the Myers-Lawson School, you know, that worked very seamlessly as well. One thing I would just say about interdisciplinary collaboration is that it's a wonderful thing, but a lot of it's really about relationships. It's about finding people that ultimately you can work with. I have plenty of people that I would consider my friends, but that I could never work with. And maybe this rings true to others. So again, relationships do matter with interdisciplinary work.
Well, thank you so much. We're at time. Yes.
One other question.
Oh, sorry, was there one online? We'll do a quick one. Your study of, this is from Ben. He's watching online.
Oh, hey, Ben. Hey, Ben.
Your study of form and texture is so enlightening. Making the cooling visible and appealing is terrific. Can you describe the role of the designer for a project like this versus an engineer? And how do we convince funders the criticality of having both perspectives on a project? Thank you.
Sure. Well, I mean, for that, I felt that it was absolutely essential to have someone like Georg Reichert, because he's someone who studies evaporative cooling. It's part of his research, and he was really a reality check for us, that we weren't just thinking in science fiction fluff. And so to pursue additional funding, which we're looking at right now, I think we would need to expand that. I didn't show a lot of the testing regimens that we did in much detail, but they were all set up and provided a lot of the equipment by Georg Reichert, who we're indebted to. But so yes, that's needed. You need some kind of proof of concept, some data, if you're claiming your cooling space. So by how much? Yeah, with different measures of efficacy.
Great, thank you. As we are at time, and so I want to thank you, Brooke, for sharing your work with us today. I want to thank you all for coming and spending some time with us this morning at ICAT. I think there may still be a few donuts over there, I haven't checked, but feel free to continue the conversation. And we'll be here next week, same time, same place, with more donuts. And I hope we'll see you then. Have a great weekend. Thanks so much.
Great to see all of you in architecture here. I hope you keep coming back.